The most incomprehensible thing about the world is that it is comprehensible. Albert Einstein. That's true. The whole of science is nothing more than a refinement of the everyday thinking. Albert Einstein. Energy and persistence conquer all things. Energy and persistence conquer all things. Benjamin Franklin. That's right. Now, there are some issues with this model. For example, if you have these quark things and if they are real, they are slightly unusual little particles. How come we've never seen a quark running through a bubble chamber? Just one? How come we've only seen the three of them bound together? Or a quark and an anti-quark? We've never seen a pair like two quarks. We've never seen four of them, and certainly we've never seen one all by itself. That was a big puzzle in this early era in 1964, and in fact for many years, this quark model was dismissed by the most physicists as a sort of interesting, had some useful features, but it couldn't be true. Even Murray Gell-Mann would give talks and say, I don't really believe that quarks are real. I just think they are a mathematical construct which help us to organize this zoo of particles and understand that it's not so complicated after all. All these patterns, the octet and the triplets, and all these grouping of particles can be understood in a simple way. So, as usual, you come up with this radical hypothesis of the new particle, and then you are timid about proposing that's real. It's like a Mr. Dirac. That's like Mr. Dirac who is afraid to believe that his equation, which predicts antimatter, is predicting something real, or Mr. Pauli, who's afraid that his postulation of the neutrino is really something real. At first, people tend to think, well, it's just a mass. And then, as evidence began to grow, people begin to view the object in question as something real. So we are going to be talking in this lecture and the future lecture about growing evidence for the reality of quarks. Quarks are actually a little point-like object that buzz around and can walk into things. And in fact, nowadays you can see tracks in the bubble chambers that aren't directly from our quark, but indirectly from the quark. It's extremely powerful evidence for the real existence of these things. Let's talk more about adding up the property of the quarks to get the properties of the objects themselves. Let's think about mass for a second. If a proton is 3 quarks, 2 ups and down, you have to ask yourself, okay, what's the mass of each of those 3 quarks? This is a subtle story which got modified over the years, but in the Gell-Mann's day, he suggested that maybe the up and down quark were very similar to each other, each of them carrying out 1/3 of the mass of a proton. So you put 3 of them together and you get a proton mass, okay? Now, if the up and the down quarks are similar in mass, then what would happen if you put an up and a down together? That would be the neutron, and according to this quark model, since up and down weigh about the same, the neutron and the proton should weigh about the same. That is why they are the same size! And they do. Yes! So this model explains why certain particles come in pairs or partners. Similarly, the 3-pi mesons can be understood as just a different combination of the up and anti-down or down and anti-up, but they are all going to weigh about the same. And indeed, the 3 pions from the little lovely triplet which weighs about the same. So again, this model has some simple premises, and once you've written them down, you are inevitably drawn to the conclusion. Then the question is, does the data match? And it does. Time after time, experiment after experiment, the data matches the prediction of the simple model. How about electric charge? these are the little particles. They have to have some kind of electric charge on them, and Gell-Mann kind of works out what it should be, and says, okay, here's my model. The up quark has a charge of 2 thirds. The proton is 1, the electron is negative 1. My up quark is 2 thirds, and my down quark is a negative 1 third. So is there the strange quark? So this is weird, kind of the creeping people out. In fact, I think that the reason alone was why Gell-Mann didn't quite believe in the reality of his quarks, because nobody had ever seen an object in the laboratory that had a spin, electric charge 1/3 or 2/3. That would leave a very distinctive pattern in the bubble chamber. The more charge you have, the density of the bubbles effectively changes. You can really tell what the electronic charge of the object is. It would have a really clear signature if you had an object of the charge 1/3 and nobody had ever seen anything like that, right? So Gell-Mann says, well, it's okay, because in my model, the quarks always come earlier in pairs or in triplets, and so let's think about a proton and up and down. So that's a charge 2/3 and another 2/3 and then minus 1/3. Do the arithmetic. 2/3 plus 2/3 minus 1/3 is 1. So the charge of the proton works out. Wow! And a neutron would be an up and down, so that's plus 2/3 minus 1/3 minus another third gets you to 0, which is the electric charge of the neutron. Yes! So at first it looks like a numerology, but you don't have any room to fudge. Now you are stuck. Every other particle's charge is predicted. So you can check if it agrees. And it does. The whole zoo, hundreds of particles. All these quantum numbers are adding up and making sense. It's a coherent picture. It's a nice little model. Wow. This model has been improved over the years since 1964 and deepened. We are going to have to talk about the ways that this model moved from the crude picture to real, formal mathematical theory, but it certainly gave people a pause. They looked at the model and everybody was intrigued by it. It was nice to think that the world really is simple and that there is not 100 fundamental particles of the nature. So I think although at first people didn't necessarily believe in it, there was a lot of skepticism about this Koch model. People were at least willing to challenge it and test it. It was kind of the working framework that you could compare data with, and it continued to succeed every time you tested it, right? This model has some predictive power. So, for example, let's talk about this strange Koch. Why did he call it that? Well, remember, people had been finding some strange tracks in the bubble chambers in the 1950s. They didn't quite make sense at first. Indeed, it was Murray Gell-Mann in the 1950s who proposed that there is a new property of matter, a new quantum number, like electric charge, but different, which he calls a strangeness number because it told you how strange these tracks are. Yes. It was always in an integer, 1 or 2 or negative 1. And with every particle in the zoo, when people were tabulating the properties, they had tabulate its mass, its lifetime, its electric charge, and its strangeness number. And now, in the quark model, here is the explanation for a strangeness number. Just count up how many strange quarks are in there. If you have a baryon, that's up, down, strange. That should be a particle with a strangeness 1. If you have a particle that's up, strange, that would be a particle with a strangeness 2. And again, it matches the data very beautifully. The strange quark would have to be a little bit heavier than the up and down, because the strange particles were a little bit heavier. But you can make predictions. By looking at an up-down strange, you can estimate the mass of the strange quark, and now you can make a prediction about the mass of an up strange object, and that's exactly what its mass turns out to be. Nice, convincing evidence that this is a good model. Here is a really interesting idea. What if you had a particle that was strange, right? You can build any combination of the three you want. That would be a triple strange baryon, and nobody had ever seen such a thing. So this is like 100 years earlier, when the Mendeleev first makes his periodic table of the chemical elements and says, "There is a hole here. I believe that the nature should fill that hole. There has got to be some material," which later turned out to be a germanium, and he was correct. Yes. It's a similar story here. There is a hole in our new little periodic table, if you like, of quarks building up the baryons and mesons. Let's go look for a triple strange object, and it was found. It's called the omega particle. Omega is the last letter of the Greek alphabet, and in a certain sense, this is the last particle that you'd have expected based on this model. Of course, there have been many more particles since then that we'll be talking about. To be honest or fair, the omega particle was actually discovered and predicted a little bit before the quark model, because Murray-Gell-Mann had come up with what he calls the eightfold way, which was simply an observation of the patterns that a quark's model explains. So really, the quark model retro-dicted rather than predicting the existence of the omega. It made such a complete sense and fit in so well that I think the discovery of omega particle really was pretty good. Wow. I will not call it a clinching argument for the quark model. At least it left people with a sense that this is a visible model. The strange quark is a little bit a funny particle. It is a strange particle. For one thing, it's heavier than the other two. For another thing, its electric charge is the same as the down quark, so it kind of looks like a heavy partner of the down quark. We've seen this before. We've discovered a muon, which is a heavy partner of an electron. In fact, oftentimes when we discover particles, we discover that they have a heavy, I don't know what to call them, heavy family members. It's another particle of the nature that's a lot like it, but radioactive and heavier. The down quark is the stable one, and the strange quark decays weakly into a down quark or into the up quark, it turns out. This is just a sort of an interesting curiosity. It's kind of another who ordered that situation. Why do we have a strange quark in nature? Are there strange quarks in the ordinary world? Not very many. Your body is made mostly of the protons and the neutrons, which are ups and downs, in fact everything in the world around you. To an extremely large approximation, it's just up quarks and down quarks, which build the protons and the neutrons, which build the nuclei of atoms. And then there is electrons, and that's all you need. So, protons, neutrons, and electrons are still perfectly valid way of thinking about how the world is made of. But if you want to look at the simplest level, then you should think of ups and downs and the electrons, and that's the light particles. They tend to be quite stable. And then we've got these heavier, somewhat more mysterious particles. They are real and they occur in nature. They occasionally occur in the cosmic rays. There are stars that people believe have strange quarks in them. This is an active field of research in astrophysics. Some of my own nuclear physics research is looking into the amount of the strange quark content in the ordinary matter. There is always going to be some small probability that, for example, a strange, anti-strange pair will pop into existence inside of the proton. So I'm investigating the strangeness of the ordinary matter. I might be strange. I might be a strange particle physicist if this stuff turns out to be correct. So people are still investigating the details of this story, but the fundamental idea was proposed in the 1964 and is still part of our standard model of particle physics today. Sure. It's not the end of the story. What we are going to discover is that there are more particles, and we are going to have to try to fit this stuff all together. In particular, I haven't yet said word one that about the forces that binds quarks together. Right now we have a very descriptive model. It's kind of the Johannes Kepler taking this mass of data about the planets and saying, aha, they form ellipses. Very elegant. So I think that's what Murray Gell-Mann has done by creating this model of quarks inside of the proton and neutrons and their pions and so on. And what we are still lacking, and what's going to come next is a real theory, like Isaac Newton said. But we can understand that elliptical orbit as arising because there is a universal law of gravity. So what we are really looking for is some underlying theoretical mathematical framework. The quarks will be players, just like the electrons were players for QED. We are going to look for the analog of the theory of quantum electrodynamics for this new strong force of nature that creates the baryons, the mesons, the hadrons that build up nuclei. Wow, thank you!